Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Martian slopes Likeky caused by dust, Moon's uneven interior and evolving dark matter. Martian slope streaks likely caused by dust, not water. A new study has challenged the long-standing idea that dark streaks seen on the slopes of Mars may be caused by liquid water. For years, planetary scientists have been intrigued by these mysterious features, dark, finger-like markings that appear to creep down dusty Martian cliffs and crater walls. These streaks, first captured by NASA's Viking mission in the 1970s and more recently observed by the Cassis camera on ESA's ExoMars Trace Gas Orbiter, had been interpreted by some as signs of water flows, potentially even pointing to environments where life could exist today. However, new research from scientists at Brown University and the University of Bern suggests a different story. Instead of flowing water, the evidence now strongly points to dry avalanches of dust, triggered by wind or impact events. The team, led by Valentin Bickel and Adumas Valentinas, used a machine learning algorithm to build the most comprehensive map yet of these slope streaks, analyzing more than 86,000 high-resolution satellite images and cataloging over 500,000 individual streaks across the Martian surface. By cross-referencing this data with environmental factors like temperature, wind speeds, humidity, and geological activity, they found no patterns supporting the presence of liquid or frost-related processes. Instead, they discovered strong associations between streak formation and dry conditions, particularly areas with high wind activity and recent dust deposition. Some streaks were found to be more common near recent impact craters, where shock waves may loosen surface dust, while others appeared in regions prone to dust devils or rockfalls. The researchers concluded that these features are most likely formed when fine layers of dust suddenly slide down steep slopes, creating the dark, temporary markings seen from orbit. These streaks, some of which last for years while others fade more quickly, are likely part of ongoing dry geological processes that may transport millions of tons of dust every year, possibly playing an important role in Mars' climate system. Importantly, this new understanding diminishes the likelihood that these streaks mark currently habitable environments, easing concerns about contaminating sensitive sites with Earth microbes brought by future missions. This also underscores the usefulness of big data and machine learning in planetary science, allowing researchers to eliminate some hypotheses without the need for immediate on-site exploration. Ultimately, while the dream of discovering present-day Martian water remains compelling, this study significantly shifts the focus toward understanding Mars as a planet shaped more by wind and dust than by water. Moon's uneven interior explains Nearside-Farside differences. The Moon's two faces, the familiar near side that always faces Earth and the more mysterious far side, have long puzzled scientists with their stark differences in appearance and composition. The near side is darker, smoother, and marked by vast plains of ancient solidified lava, while the far side is more rugged, heavily cratered, and lacking in those widespread volcanic features. For decades, researchers have suspected that these visible contrasts might be due to differences deep within the Moon's interior, but direct evidence has been elusive. Now, using precise data from NASA's Gravity Recovery and Interior Laboratory mission, or GRAIL, which involved two spacecraft named Ebb and Flow, scientists have made a compelling discovery that may explain the mystery. They detected a subtle but significant difference in the way the Moon's mantle, the layer beneath the crust, responds to stress on each hemisphere. Specifically, they found that the mantle on the near side is 2 to 3% more deformable than on the far side, suggesting it is also warmer by as much as 170 degrees Celsius. This difference in deformability was derived from careful measurements of the Moon's gravitational field as it responds to tidal forces from Earth, allowing researchers to peer into the Moon's inner structure without needing to physically land on its surface. The team, led by Ryan Park, developed models of the Moon's interior and showed that the observed differences could be explained by a thermal imbalance between the two sides. According to their analysis, this heat difference could stem from the presence of radioactive elements like thorium and titanium concentrated in the nearside mantle. These elements generate heat as they decay and may have kept the nearside warmer over billions of years. This lingering warmth could be a leftover effect from the same internal processes that fueled extensive volcanic activity on the nearside between 3 and 4 billion years ago, while the cooler far side remained less geologically active. The findings, published in the journal Nature, offer strong support for the theory that the Moon's asymmetric surface features are the result of uneven heating and internal composition, rather than external factors alone. Importantly, the method used in this research, measuring subtle gravitational shifts from orbit, can be applied to study the interiors of other celestial bodies as well, including Mars and the moons of the outer planets like Enceladus and Ganymede. Since it does not require landing a spacecraft, it presents a powerful tool for probing the hidden interiors of distant worlds and understanding how their internal dynamics shape what we see on the surface. Evolving dark matter may help solve the Hubble tension. A persistent mystery continues to challenge our understanding of the cosmos, lurking right at the center of the standard cosmological model. While all current observations confirm the idea that the universe is expanding, a puzzling inconsistency has emerged between measurements of that expansion in the early universe compared to more recent, local measurements. The rate of acceleration derived from the early universe appears to be slower than what we see closer to the present day. This discrepancy, known as the Hubble tension problem, remains unresolved despite numerous efforts to explain it. Over the years, scientists have floated a wide variety of ideas to address the issue. Some suggest that Einstein's theory of general relativity might need revision. Others wonder whether dark matter truly exists, or whether time itself might not tick at a uniform pace throughout the cosmos. There are even speculations that the entire universe might be rotating in some subtle way. Now, a new idea enters the fray: what if dark matter itself changes over time? While evolving dark energy has been studied in some detail, the idea that dark matter could evolve hasn't attracted much attention. That's largely because current observations support the existence of a stable, non-interacting form of matter, dark matter, that influences the cosmos through its gravity but does not emit or absorb light. Though we haven't directly detected dark matter particles, the gravitational effects they produce match observations of galaxies and large-scale cosmic structure quite well. Most researchers skeptical of dark matter's role prefer to discard it altogether in favor of alternative explanations like modified gravity, rather than trying to tweak its properties. However, the new proposal suggests that instead of being completely stable, a portion of dark matter could change over time. The researchers explored a model where both dark energy and dark matter might evolve, but found that varying dark matter alone offered a much better match to the data. Their work is built on the idea that what we observe in the universe, how it expands and evolves, depends on the balance between energy and matter. If dark energy is held constant but dark matter is allowed to evolve, the effects can resemble those produced by a model with constant dark matter and evolving dark energy. They proposed a form of dark matter with a changing equation of state. Essentially, its behavior in relation to pressure and energy density shifts over time. To be consistent with observations, this equation of state would need to oscillate. While this might sound speculative, it isn't entirely unprecedented. Neutrinos, for example, have mass, don't interact strongly with light, and are a form of hot dark matter. They also exhibit oscillating properties in terms of mass. If cold dark matter particles had a similar oscillating behavior, it could account for the observational mismatch. The model that best fits the data, according to the researchers, is one where about 15% of cold dark matter behaves in this oscillatory way, while the remaining 85% remains standard and stable. This hybrid model would help reconcile the difference between early and late measurements of the universe's expansion rate without undermining our current understanding of how dark matter behaves on large scales. It's important to recognize that the proposed model is still in the realm of theory, a toy model meant to explore possibilities rather than provide final answers. The researchers themselves acknowledge that their approach is broad and doesn't pinpoint specific physical characteristics or particle candidates for this oscillating dark matter. Even so, their work opens up new avenues for thinking about one of cosmology's biggest challenges. It expands the landscape of theoretical models and suggests that the concept of evolving dark matter may be more than just a fringe idea. In the ongoing effort to solve the Hubble tension, this line of inquiry could be one more step toward understanding the deeper mechanisms shaping our universe.